Hello student, welcome back to lecture series on Fourier transform. In my today's video, I'm gonna explain to you all convolution theorem for Fourier transform. Okay, so we go for convolution theorem for Fourier transform. It is one of the important theorem here in Fourier transform. Okay, yes. So if you are interested to see similar videos, guys, go and check in my I button. Okay, you will get the similar videos there. So let's get dive into our today's lecture. So first of all, I'm going to explain to you the statement for theorem. Okay, we go for the definition of convolution. Okay, yes, I written here first of all the definition for convolution theorem. Okay, so this one is the definition for convolution. The definition, it says that the convolution of a two function. Okay, so for example, if your f of x and g of x are the two function, like I consider f of x and g of x are the two function. Okay, so as we are taking Fourier transform, that means obviously interval minus infinity to infinity remains same. Okay, so we are defining convolution on a two function f of x and g of x. Okay, so we write the dot product, okay, or f of x dot g of x. Okay, we write f of x dot g of x as the interval minus infinity to plus infinity f of u g of x minus u du. Okay, and if you want, you consider this one as a h of x. Okay, that means give some name like h of x, g of x. Okay, something like this. So already we have some of the function here. Okay, I consider two function f of x and g of x. Okay, so their integral I written this one. Okay, so this one is the definition for convolution theorem. Okay, nothing than this. Yes, so we are going to apply this definition for solving our convolution theorem. Okay, so this one is a definition for convolution theorem. Okay, but in actual our convolution theorem statement, it is here. What is the statement for convolution theorem? It says that the Fourier transform of a convolution of f of x and g of x. So we write Fourier transform of convolution of f of x and g of x as the product of their transform. Okay, yes, so Fourier transform over f of x over g of x. Okay, that means f of x star g of x can be written as Fourier transform of f of x dot Fourier transform of g of x. Okay, yes, so this one is a statement for convolution theorem. Okay, this one is the entire statement for convolution theorem. Okay, so by using this definition, we are going to prove this convolution theorem. Okay, yes, let me write the definition for Fourier transform over here. So Fourier transform over small f of x, okay, can be written as minus infinity to plus infinity. Okay, small f of x e raised to is x dx. Okay, yes, this one is the definition for Fourier transform. Okay, yes, so we are going to use this definition here for solving. Okay, and let me write convolution for two function f of x and g of x. Okay, okay, so I am going to use this definition over here. Okay, yes, so here we are going to use this definition for convolution of a two function. Okay, yes, so f of x star g of x, let me write that function. So see that how I'm going to define it here. As we want the f of x star g of x here, f of x star g of x, so we only going to apply Fourier transform to the both side. Okay, yes, so by definition of convolution, okay, by definition of convolution theorem, okay, by definition of convolution theorem. So as we have f of x star g of x, okay, f of x star g of x, which can be written as integral over minus infinity to plus infinity. Okay, minus infinity to plus infinity. I am writing that the convolution definition as it is here, that I am going to apply here for finding the Fourier transform. Okay, for this two property. Okay, so this is the property. Actually what it says, that it is the product of their transform. Okay, so Fourier transform can be written as product of their transform. Okay, yes, so let me write this one, f of u g of x minus u du. Okay, so I written this one is the definition for convolution of a two function. Okay, but what actually we want the Fourier transform of f of x star g of x. Okay, that means what we want the Fourier transform of f of x star g of x. Okay, so if you are taking Fourier transform of this side, obviously apply Fourier transform of this side. Okay, Fourier transform of this side. Okay, so what I have done, I just apply Fourier transform to the both side of our convolution definition. Okay, definition of convolution. Okay, yes, I applied only the Fourier transform over here. Yes. Now see that, consider this one as an entire function. Okay, consider this one as the function. Okay, f of x we consider. Now what we have here, we are going to apply this small f of x as an entire bracket. Okay, entire bracket I consider small f of x. So wherever small f of x is there, replace this integral. Okay, so we get the double integral over here then. Okay, so Fourier transform, it can be written as, okay, minus infinity to plus infinity, that integral it remain as it is. Okay, minus infinity to plus infinity as it is. Okay, small f of x, I'm going to replace this entire integral. Okay, so under bracket, let me take my integral minus infinity to plus infinity small f of u g of x minus u du. Okay, this bracket interval complete. Okay, so I replace this one as a f of x here. Okay, yes, so this one is f of x e raised to isx dx. Okay, let me write e raised to isx dx. I hope you all have understood, guys. It is not that difficult. Okay, this one is only the f of x. I consider this entire bracket as a f of x and I replace here in this integral. Okay, so minus infinity to plus infinity as it is. This f of x I replace here, e raised to isx and dx it is here. Okay, yes. So what we do, we are going to change the order for our integration. So we are going to change the order for integration. Okay, so we are going to change the order for integration, as we have du and dx here. That means integral over du also present and integral also over dx also present. Okay, so but first of all I am going to solve this integral with respect to dx. Okay, so change the order of integration. Okay, so take du outside, dx inside, e raised to isx also it is coming inside. Okay, so now see that if you are taking du outside, that means f of u it goes to the constant with respect to dx. Okay, so I'm going to take minus infinity to infinity f of u outside here. Okay, f of u it is going to be outside. I'm just changing the order for integration, guys. Okay, this is the standard rule for changing the order of integration. Okay, so I have taken f of u outside. Under integration minus infinity to infinity keep as it is. Okay, and the remaining term, okay, the remaining term try to build it for the x. Okay, so g of x minus u, okay, g of x minus u keep as it is having x term present here. Okay, e raised to isx it is also take it inside. Okay, and a dx also inside. Okay, this one, and a du will take it as the outside. Okay, now see that how I have changed the order for integration. Okay, first I'm going to solve the integral over dx. Okay, as we raised to isx present, g of x minus x it is also present, so I'm going to change the order for solving our dx first. Okay, and then we go for the du here. So I replace dx and du here. Okay, so with respect to dx now, f of u it is going to be a constant, so I taken it outside here. Okay, minus infinity to infinity as it is there, and all the term for with respect to dx keep as it is here. Okay, g of x minus u which comes with respect to dx, and e raised to isx which comes with respect to dx. Okay, so I taken under this integral and du outside here. Okay, yes, now see that I'm going to solve this integral here. Okay, first of all solve this bracket. Okay, it is way easier to solve the bracket. Now see that as it is having function under function, g of x minus u, that means g under x minus u, function under function. So we go for the substitution. Okay, so what we do, we substitute x minus u which is equal to t. Okay, so we are going to substitute x minus u which is equal to t. So replace that x also, replace dx also. Okay, so we write the value for x. What is the value for x? T plus u. Okay, if x minus u as a t, then we write the value for x is a t plus u. Okay, yes, so you have to replace dx also. Okay, so in order to replace dx, take the differentiation of both sides. Okay, x with respect to differentiation of x which is a 1. Okay, this one is 1, minus u with respect to x it goes to 0. Okay, and dt having differentiation dt by dx with respect to x. Okay, dt by dx. So we write dx which is equal to dt. Okay, so now see that I taken dx here, dt keep as it is. Okay, yes, so what we do, we are going to replace these values in our integral. Okay, yes, so what we do, minus infinity to plus infinity f of u keep as it is. Okay, we are replacing only the value for g of x minus u. Okay, yes, g of x minus u means again integral here, minus infinity to plus infinity. Okay, so g of x minus u can be replaced as g of t. Okay, so I replace x minus u as a t. Okay, g of x minus u, it is here g of t, e raised to is, okay, the value for x is a t plus u. Okay, t plus u. So I'm going to replace that x also, and the value for x, which gives us the t plus u. Okay, e raised to is into t plus u. Okay, and dx can be replaced as a, we are going to replace dx as a dt. Okay, this is an entire replacement. Okay, entire replacement of the terms. Okay, and a du outside here. So why I'm replacing the quantity here, guys? Because x minus u comes under g, so function under function, it gives us the value. So in such a case, for solving integration, we try to go for the substitution in order to take that x minus u out from here. Okay, yes, so I just go for the replacement of values. Okay, and then after that we go for solving this step later. So what is the next step possible here? So as we have integral g of t e raised to is into t plus u dt and du. Okay, so u, it is here the term u which is constant here with respect to dt. So we are trying to take that u outside from this one. Okay, so multiply e raised to is under bracket, which gives us e raised to ist and e raised to isu. Okay, so I'm going to write this step here, e raised to ist into e raised to isu. E raised to isu. Now see that how I have written. I multiplied by is to that t and is to u. Okay, then e raised to ist it is here, e raised to isu here. So I made this exponential term to both are separate. Okay, so when we have two different exponential term, we add their power. Okay, yes, this way I written this step. Okay, now replace these values here. Now with respect to dt, e raised to isu, it is a constant here. So I'm going to take it outside here. Okay, yes, let me take it to the next page. Okay, so we are going to write minus infinity to integral minus infinity to plus infinity f of u e raised to isu. Okay, e raised to isu is it is constant here, minus infinity to plus infinity. Okay, g of t e raised to ist. Okay, e raised to ist dt. Okay, this integral complete, and outside du over here. Okay, now see that, guys, I just taken that e raised to ist inside here and e raised to isu outside here. Okay, so inside we have here only the term of t present here. Okay, only the term of t which is present. So okay, so we go for the next step. So in our next step, as we can see, okay, as we can see here, e raised to isu f of u du, it is integration complete. Okay, but under this integral we got the another constant integral. Okay, minus infinity to infinity g of t e raised to ist dt. Okay, with respect to du, this one is an entire constant term. Okay, with respect to du, so take it outside from this integral. Okay, so now see that how I am going to take this one as outside. Okay, yes, take this one outside, minus infinity, integral over minus infinity to plus infinity g of t. Okay, e raised to ist dt. Okay, this one the integral I taken it outside. Okay, dot. Okay, multiplication is between them now, so I'm going to write minus infinity to plus infinity f of u e raised to isu du. Okay, so this one is the, I made these two integrals separate over here. Okay, g of t e raised to ist dt and f of u e raised to isu du. Okay, yes. So when we are going to apply definition for Fourier transform. Okay, when we are going to apply definition for Fourier transform, then what we get here? Okay, yes, now see that one more thing, as we don't have t. Okay, as we don't have t present in our given Fourier transform. Okay, so we are going to reverse our terms. Okay, so how we are going to reverse the term here? As per the standard form of integral, we can replace their variables, g of t e raised to ist dt. So let me write that for rule here for your understanding. Okay, integration, okay, g of x dx, which is equivalent to integration of g of t dt. Okay, that means whenever we replace x and t here, dx as a dt and g of x as a g of t, our integral it remains same. Okay, these two values are remain same. So that I'm going to apply over here. Replace t as a x here. Okay, as we have to prove f of capital F, that means Fourier transform f of x star g of x. Okay, Fourier transform f of x star g of x is equal to your Fourier transform over f of x into Fourier transform over g of x. Okay, so I'm going to replace only the value t as a x and u as a x. Okay, not an issue, you can replace the values. Okay, minus infinity to infinity g of x e raised to I s x, okay, dx multiplied by minus infinity, okay, minus infinity to plus infinity f of x e raised to I s x dx. Okay, yes. Now see that this function represent the Fourier transform of g of x. This function represent Fourier transform of f of x. Okay, so I'm going to write Fourier transform of g of x dot Fourier transform of f of x. Okay, this one is a Fourier transform of g of x and this one is a Fourier transform of f of x. Okay, so what we have to prove here in our given convolution theorem, Fourier transform of f of x star Fourier transform of g of x. I consider that one here. Okay, Fourier transform f of x star Fourier transform of g of x. Okay, I consider at the initially this one here, and we have to prove this one. Okay, so what I got here, Fourier transform of, okay, f of x star for g of x. Okay, Fourier transform of f of x star g of x can be written as Fourier transform of f of x star Fourier transform of g of x. Okay, this one is our required proof for our given properties. Okay, property. I hope you all have understood, guys, the convolution theorem, not that difficult. I just need a little variable changing. Okay, yes, one of the easy way, easy proof we have here for convolution theorem. Okay, it is only the little complication you will get where you will get the complication when we are replacing, or when we are using variable property of changing the order of integration. Okay, property of changing the order of integration that we done it here. Okay, I taken dx inside, du outside. Okay, this one is a little just confusing, but I hope you all have understood. Okay, not that difficult, it is one of the easy theorem. Okay, so for your reference you can note it down my entire theorem over here. Okay, it's one of the easy theorem, guys, not that difficult. Okay, so I hope you all have understood the convolution definition here first, and then I applied that definition for finding the Fourier transform for two function f of x and g of x. Okay, so we can call this one as a convolution theorem for Fourier transform. Okay, I hope guys you all have understood convolution theorem for Fourier transform. Okay, that's it for our today's lecture. I hope you all have understood everything. So thank you everyone, thank you for my today's lecture.